In this video, I will give you some hints on wet gasification. I am Anne Roubaud. I am working as an engineer and researcher at CA since 2005, and I am a CA expert in the domain of hydrothermal processes. LITEN is a research structure focused on new energy systems development. It is mainly based at CA Center in Grenoble in the French Alps. Our role in the Pulp and Fuel project was to develop wet gasification for the valorization of black liquor for hydrogen production. This hydrogen will serve as a complement for the fuel synthesis from the syngas produced by the dry residue gasification. Black liquor is the effluent of the wood cooking after the cellulose recovery for the pulp production. The black liquor contains lignin fragments, some sugars, and the remaining cooking chemicals. In the case of craft cooking, the cooking chemicals are soda and disodium sulfide. This is an aqueous solution with 20% of dry matter in average, corresponding to a carbon content of 60 grams per liter. The ash content is high with 72% of the dry matter, corresponding to a low energy content, but on the other hand with a high sodium and sulfide concentration. Moreover, this is a corrosive solution with a pH of above 13. Wet gasification is a thermal process performed in supercritical water conditions. It means at condition above the critical point, so a pressure above 221 bar and a temperature above 374 centigrade. In those conditions, the organic matter is recovered into a mixture of gases with mainly hydrogen, methane, and carbon dioxide. But on the other hand, the inorganic species will precipitate due to the strong reduction of their solubility in the supercritical water, having a low dielectric constant. The gasification conversion is following different steps. The first is the hydrolysis of the biomass, producing monomer compounds. Those monomers are transformed by dehydration and decarboxylation to form organic intermediates. They undergo further degradation and condensation into the formation of gases and char. The char is a solid matter of high carbon content, and some organics remain in the aqueous phase. Further reaction between gases and water, like methanation, and water-gas shift reaction results in the final gas composition. Now we will have a look at the behavior of black liquor, specifically the production of gas from the organic matter part. The gas yield here are expressed by the division of the weight of gas with the initial dry matter of black liquor, or the dry ash-free matter. It means the dry organic matter, in fact. One can observe that the gas yield is increasing with the temperature. Below the critical point of water, yields are very low. The mass yield is 55% at 600 centigrade. Regarding the gas composition, you can see here some results obtained in batch reactor, and on the graph you have the results at 500 centigrade. Hydrogen and methane are produced in the same ratio, but at 600 centigrade the methane is favored. Ethane is also formed in a non-negligible quantity. Looking at the inorganic part behavior, as the black liquor is rich in sodium, it will combine with the CO2 produced by the gasification to form the sodium carbonate. But the solubility of sodium carbonate is divided by 200 going through the critical point, so it will precipitate. This was confirmed by injection tests of sodium carbonate in our continuous pilot. This precipitation behavior is the reason why a salt separator is needed in the case of high inorganic content resources or a specific design of a reactor. As sulfur is also an important part of the craft cooking chemicals, we must have a look where it will be recovered. Our experiments show that it will be mainly recovered into the aqueous phase for all the tested temperatures. Some hydrogen sulfide is formed at the highest temperature. Now, if we want to design a continuous process, we must take into consideration different needed steps. First, the feeding of the process with the resource to be converted, and then the pressurizing and the heating. The desired pressure, temperature, and flow rate must be reached in the conversion reactor during a defined residence time. Then it flows through the cooling system. It is depressurized, and then the different product phases are separated. In the case of black liquor, the following process concept is proposed, with a pump feeding the black liquor at the 300 bars. Then the solution goes through a first step of conversion into a salt separator, heated at a temperature such as 400 centigrade. This salt separator is needed to avoid the plugging of the following part of the process under temperature. Then the fluid phase is going into the gasification reactor at a temperature between 600 and 700 centigrade, still under the pressure. The desired residence time in the reactor is 5 minutes. After conversion, the fluid is cooled down and then sent to a first phase separator, still under pressure, to separate the permanent gases, like hydrogen and methane, from the liquid phase. Then the liquid is depressurized to allow the CO2 to be left out under the gas phase, and the aqueous phase is recovered at the bottom. In conclusion, we can say that the wet gasification of black liquor is feasible, but with the use of a salt separator to avoid any plugging of the reactor, and also to recover the cooking chemicals of the craft process. We have obtained a 79% of recovery of sodium. On the other hand, sulfur is mainly recovered in the aqueous phase. For the gas production, temperature is the main influencing parameters for the gas yield and also for the gas composition. And our best conversion results were obtained at 600 centigrade. I thank you for your attention.